take the 4 neighbors, take the average or max or whatever. So this is easy. This part is easy. All we are doing is simply rearranging the numbers. Then the rest of it is our regular neural network. So forward pass is extremely easy. Right?
Actually, we can use the second equation for the first one also, instead of having it two different. This way we can generalize for 3 different channels of the image.
Correct, correct. But just for clarity, I put it over here. So as Michael said over here, let me elaborate what Michael said. Here we were doing a summation from 1 to 4, correct? Because there's a 4 summation going on over here. We could also think of it this way, that over here there's a summation of 1 going on over here. But if we had color channels, there will be summation of 3 going on over here as well. Okay. So this way we can generalize it. So in fact, in the code, that's what I do. So once I build it. Okay, so to finish the forward pass, okay, so this was the pooling in the second layer, dividing by 4, summing the 4 neighbors. Okay, then the flatten over here is my 16 by 6 equal to 96 over here. So we multiply by the weight plus the bias, apply the activation. So this is the output of the hidden layer, then this is the output of the actual output of the output layer, where the input is coming from the previous layer, correct? Multiplied by the weights, biases, so this is regular, okay? So, like I said, previous lecture, back propagation was the key part over here. So let me go over the back propagation briefly. Okay, okay, so let's start from, because in our example we are doing a digit recognition, right? So how many outputs do we have? 10. So what kind of activation function will we use typically in the last layer? Softmax, which we already had done the derivation. So what's the delta in the last layer? Simply the sum minus the actual, right? Okay, so let me now take you to the picture briefly and see if this is making sense. Okay, so now let's start the back propagation. Okay, so the delta over here is S minus Y, correct? Is the delta in this softmax layer. Okay, so now if we have to compute, see this is W2. If we have to compute partial L over partial W2, so remember how will that be computed? Delta times what? Delta in the last layer multiplied by
The input of the last layer.
if you recall, this will be basically partial SI over partial whatever is W2 over here, right? Which in W2, if you take a look, was, sorry, not W2. Let me just call it S. So S, if you recall, the sum over here, right? The sum over here, the sum over here was, my mistake, the A1 W2 plus B2, right? So if you did a partial with the W2, what will happen? It will give you the previous output, right? Remember the previous output over here we are calling A1. We're calling this A2. Very similarly, if I go further, what will be part? Then once we have computed the delta here, which will further multiply this by the activation, derivative of the activation, then further, what's the previous output over here?
The flatten out 90.
The flatten. Okay, exactly. So hopefully this is straightforward. Okay, so let's see if you agree this part. Delta W2 equal to, right? So this is basically the delta in the last layer multiplied by this, which is the previous input feeding to the last layer. And what's the previous input? That's the A1, right? And we'll do typically the transpose, and if your matrices are incorporating the batches, then this will slightly change. But anyway, everybody agrees with this? This is the gradient with respect to W2.
Yes.
What will be the gradient with respect to V2?
That's it.
So that's just the delta. Okay. Now let's go to the previous delta. Okay, and previous delta, so I called it delta 1. Okay, so if this is, let's say, flatten over here, is the being fed over here, we call this W1, right? And if we already know the delta in this layer, okay, so we're calling this let me make this further, W2 and A2. So this is where we have the delta. So how is delta 1 related to
That
delta?
will be delta into the weight matrix into the output of previous.
Yeah, so the weight matrix comes into play, right? So delta in the hidden layer, as you can see, the weight
Weight
matrix
matrix
times the
activity.
derivative of the
Activation
activation
function.
function, because whatever, whether it's ReLU or sigmoid or whatever, right? Okay, so we know the delta 1 over here. Now let's compute delta flatten.
Oh, okay. That will be delta.
So can you tell me from this picture,
So-
how will delta flatten be related to delta 1?
That will be delta 1 into the weight matrix into, yeah, that's it.
Will there be further derivative of activation
I
function?
don't think so.
No, because there's nothing, no
Nothing,
activation involved over here. So, so as you can guess, delta flatten.
Professor, what are the dimension of delta flatten?
What is the dimension? So if you recall, we had 6 feature maps. Once we flattened, 4x4 matrix was flattened into 16 values. So, and since we had 6, the flattened dimension is 96, 16 times 6. Okay, so anyway, so let's see if everybody agrees over here. So take a look at this part over here. Delta flatten equal to delta 1, which is the delta in this layer. We further multiplied by the weight transpose to get the delta flatten. Okay, so like I said, up to here is basically standard neural network. Now it becomes more tricky. Okay, so let me ask your opinion. Okay, so let's pretend we have computed delta flatten over here. Right? So what will be the delta here then?
Could you repeat that?
Okay, delta flatten, as we said, see this was delta 1, this was delta.
Delta.
So we multiplied W2 transpose over here to get to delta 1, further multiply by the derivative of the activation function.
Mhm.
So we know this, right?
Yeah.
Then from here we went to delta flatten.
Yeah.
We multiplied this by the W1 transpose,
Mm-hmm.
but there was no derivative involved over here because it's just,
Simple. Yeah.
there's no activation involved. So we know this. My question is, now we want to know delta in this
CP2.
N of 2. So in any one of these. How will this delta here be related to this delta?
Will be the same
Simply
matrix
yes.
4 by 4.
Exactly. So as Amar said, all you have to do is, we have 16 values over here, right? First 4, put it over here. Next 4, put it in the next row. Next 4, put it in the next row. Next row. Then go over here. So there's no computation going on. It's simply, because remember, when we went forward, that's all we did. We just linearized it. So on the way back on the derivatives, it's simply putting it back in its own place.
So you're basically taking part of the delta, not the whole delta? Because the delta includes everything, all 96 input.
Yeah, so delta is 96 by 1, right? Delta
Yes.
flat over here.
So you're only taking part of the delta and map them to,
First 16 gets mapped over here, second 16 maps over here, last 16 gets mapped over here. So now we know delta CP of n of 2. So n will vary 1 to 6, so we know the delta is over here.
Professor, do we need to convert from 1D to 2D? Because from now onwards, I mean,
Yeah, so like I said, that's what we did. We basically, this was 1D over here, we converted it to 2D. So the deltas here are all 2Ds. Okay, so now my next question. We know now, let's say the delta over here. So we know the delta here, which is what we are calling CPN of 2. Delta CPN of 2. How do we go back now? What will be the delta over here?
there will be delta CP into the C1 of that is the learning parameter.
So first of all, there are 16 values over here.
So
How many values are here?
64.
So how do these get computed from here?
average.
Okay, remember when we went forward,
You need to control the pooling.
we basically took the 4 values and divided by 4.
Multiply by 4.
No, it still gets,
It's the same, right?
it's the same.
Because
Because it's like y equal to 1 over 4x, and then once you do dy over dx, it's still 1 over 4. Okay, so basically what you will do is, let me draw it a little bit bigger. So pretend here are 4 values, or 16 values. So this is basically CP of whatever, 1 of 2, right? Now as we go to 16 values, each one of these will get duplicated how many times?
4 times.
4 times. Further will be divided by what?
4.
4. So each one, and similarly the second value over here, so I'll put a different color over here, so then second value will further be divided by 4, divided by 4, divided by 4, divided by 4. Okay, and so on. So basically, there's really, this is also very easy. Every value gets put into 4 spots and then gets further divided by 4. So do we know the deltas over here?
Yes.
In all of these layers. Okay, so once again, up to this point in a CNN, it's piece of cake. The trouble starts now, okay, when convolutions are involved. So there's 2 things going on over here. As you can see, when we went from here to here, right? Not only there's a convolution going on over here, there's also a summation going on over here, okay? So how will, and there's another issue over here which I'll point out a little bit later, but first let's try to find out what is delta of k mn of 2. So what is this? How's the gradient varying. So we went over this last time, and so let me very quickly show you. It's the same thing we did last time, but hopefully now it will start to make more and more sense. Okay, so like I said over here, computing delta is tricky. An easy way to understand it, let's take a look at how we went forward. Then in the backward, we can see how the derivative will be done. Okay, so when we went forward, remember we were adding contribution due to how many convolutions?
6.
Four convolutions, right? So when we went forward, because remember the top, even though 6 convolutions were being applied to each one of the previous feature maps, but when we were summing to produce 6, we were only adding 4 of those. The top one, the second one, and so on. Okay, so this is the same equation that we had put in the forward pass, so I simply repeated that. As you can see, I said from page 3. Okay, so anyway, if we take a look at Kmn of 2, right? For a particular value of m, how many values are involved over here in our example? This is the convolution kernel, right?
24.
But this was 25, right? 5 by 5. So if we have a derivative in each one of these positions, what will be the size of this? Also 25 by 25, right? So this will also be, 5 by 5, not 25 by 5. Okay, so anyway. Okay, if we pick one particular position, so u and v, as you can see, will vary now from -2 to 2, okay, or for one particular position over here. So because now we have contributions, so let's see over here. Here's a 12 by 12, right? Okay, we do a 5 by 5 convolution, and we produce one value in this 8 by 8, right? Then what do? We move this kernel one place to the right, and then we produce the second value. So if you take a look at one of these kernel values, it was involved in computing this value. As we move this window one pixel to the right, the same kernel position value was also involved in computing this one. So each UV is involved in all these 8 by 8 computations. Okay, so that means as we work backwards, all these will be accumulated as gradients. So that's why we have this 1 to 8 involved over here. This is the delta on this side. So this is the delta over here, Cn to I of j, which is 8 by 8. Okay, so first I wrote it as a partial with respect to the kernel over here, because we are trying to, right? Okay, so then easy way to compute the partial is, let's feed in the value of Cn of 2. So if you take a look here, I basically, so this part, so this part over here, with respect to here, so the forward equation for this Cn of 2, forward equation of Cn of 2 was this sum of 4, then applying the convolution, right? Now we are taking the derivative with respect to the kernel because that's our goal, to compute the gradient with respect to the kernel. So now this is for one particular value of u and v, for one particular value of I and j. So all these three summations disappear. Because we are taking the derivative, this goes away. With respect to bias, the partial derivative will be 0. So we simply end up with okay, so we simply end up with just this term over here, because we are taking the partial with respect to k of mn. So like I said, because this is being multiplied by this term, this goes to 0, because we're taking partial with respect to the kernel. All these summations disappear because we are looking at a particular value of I and j, particular value of u and v. So, so this gets to this form. Then, as we discussed last time, okay, this is not convolution. For convolution, this should be really u minus I, because we are doing with respect to u and v. So if it was u minus v, if it was v, sorry, not u minus v, u minus I, and if this was v minus j, okay, then it will be a true convolution. And how do we switch it? All we have to do is rotate this by 180 degrees. Okay, remember once we do the convolution, we already do 180 degree rotation. So which will be exactly this. So in short, the answer, final answer is that the gradient for the kernel in the second level is the delta in this 8x8 layer. So this is Cn of 2. Okay, so whatever is the delta over here, do a convolution of this with the kernel that was feeding to it. Okay, sorry, my mistake, not the kernel, so let me draw the picture somewhere here again. Okay, let's say this is 8x8. So this is delta Cn of 2. Suppose we've already computed this. Here is a 12x12. Okay, and this is, let's say, CPM of 1. Okay, so basically what we are doing is convolution of the rotated, so we rotated by 180 degrees. Then we do this convolution on this rotated. So as you can see, if I do 8x8 convolution over here, what will be my end result?
12 minus 8 plus 1.
Which is 5x5. And this is supposed to be 5x5. Right? So, so once you get this handout, you know, it's like I said, these type of things become important, especially if you are a PhD student, you wanted to, you know, take this to the next level. So once you get this, go through it and convince yourself that this is doing the right thing. Okay. So this was basically the tricky thing. After we go through the math, we realize if it was inverted by 180 degrees, this will turn into a convolution. So basically, we inverted it by 180 degrees, changed it to a convolution. So,
Professor, I don't see why before inverting it, it is not a convolution.
okay.
Because you're still...
Yeah, so let me explain that. Okay, so see, let's say you were given two values, some kernel, And suppose the output, let me just call it Z. Z of ij. Okay, u equal to minus 2 to 2, v equal to minus 2 to 2. And say we have some image that we are doing a convolution with the kernel, right? So this is I minus u, j minus v, kernel of uv. So this is the standard formula for convolution, okay? So if you take a look, here's the I, right? So I, j are our indices for the answer of the convolution. So do you see this is I minus u, right? On the other hand, what will happen if somebody gave you this? They said it is u minus I, j minus v, times k of u. So that's not, so what I'm trying to say is this is not the convolution, because on this side we have I and j, it should be, so this is actually 180 degree rotated. Okay, so first just focus on this part. I minus u, right? J minus v. Okay. Now let me show you the part I was showing why it's not a convolution. Okay, so now take a look at this equation over here. Okay, what are our variables in our result over here? U and V, right? So, in my previous example, the summation over here was U and V, okay? But now it's I and J. So it should be U minus I and J minus V for it to be a convolution. But what do you see over here? It's the exact opposite.
So this is because we're computing the derivative in respect to delta KMN at UV.
At UV, correct.
That's why that is in lowercase.
Yeah, but we didn't write it, that's how it came out, because as we went through the forward pass, this is how it was. See over here, if you take a look, this was the convolution, right? So just focus on, so this was the forward pass. In the forward pass, we were trying to produce an answer at I of j. So that's why this was I minus u, j minus v. But once we took the derivative, right, then this whole summation disappeared. But there's an outer summation over here, which is on ij. So that basically now is no longer a convolution of these two. So once again, once you get it, go through it yourself, see if the forward pass is making sense, then you will be easily able to see. For us to turn it into a convolution, we have to rotate it by 180 degrees.
For delta C1, this is our equals values, right? Delta C1?
This one?
Yeah. This is 8 by 8, and this is...
This is 8 by 8, correct.
Okay, so in
This is 12 by 12.
Yeah. In this case, this delta is acting like the kernel that are multiplied by CBN. Because it is
So we are saying is the derivative of the kernel is obtained by doing a 8 by 8 convolution on this 12 by 12. Okay, so see, let me see if it makes sense. Let me just show you the picture. So first, see, forget the math for the second. For a second, I mean. Okay, so try to relate. We have a delta over here, right? Let's look over here. Yeah, so we are trying. Okay, so we have a delta over here. Okay, and so which is 8 by 8, correct? And we are trying to relate it to this kernel over here, 5 by 5. But if you take a look at previous, how did we get this 8 by 8? Didn't we get it once we did a convolution on the 12 by 12?
Yes.
That's how we got 8 by
So
8.
then to go back, we do
So once we go back, so our math is saying to get this 5 by 5 gradient, you have to do the convolution of 8 by 8 on this rotated 12 by 12. So if I have 12 by 12 and if I do an 8 by 8 convolution, right, what will be the answer? It will be 5 by 5. Because 12 minus 8 plus 1 is the size, right? Okay, so intuitively it makes sense that sure, only if we do 8 by 8 convolution on a 12 by 12, we'll get a 5 by 5 answer. But the fact that it has to be rotated before we do that, only when we went forward through our math and saw, that's when we realized, right? And like I was telling you last time when I did it, the implementation very first time myself, I made the same mistake as the question was asked. I looked at that u minus I and I said, oh, it's a convolution, but in reality it's not. So once I fixed that, then everything started to work. Okay, anyway, let me ask you another thing. Suppose we know the delta over here. What's the size of this delta?
8 by 8.
8 by
Okay, now from here, I needed to know this delta so that I can keep moving backwards. Sorry, this delta first. Let's go to this delta first.
12 by 20.
Or let me put it in a different color. Okay, what will be the size of this delta?
12.
Okay, so now my question to you is, from this 8 by 8, how can we go to a 12 by 12 size?
So,
12 by 12 with 5 by 5 kernel.
Okay, if I have a 12 by 12, I did a convolution with 5 by 5, what will be my answer?
It'll be less.
less,
Yes.
it will be less.
Yeah.
So that won't work.
Oh,
So now let me give you the
It
answer.
will be
Professor,
multiplied by
kernel-
C1.
Say it again. No, there's some kind of convolution going on. I'll give you a hint.
okay,
What was the question?
Okay, the question was, suppose we know the delta here, right? Which we know is 8 by 8. From here, we are working backwards. Now I wanted to know the delta over here.
Professor,
So, we know this delta has to be 12 by 12. So how is this blue delta related to the 8 by 8
Professor,
delta?
if we do a convolution on that C1,
Convolution on 8 by 8?
24 with 8 by 8.
No, but the sizes are 8 by 8, 12 by 12. Okay, let me give you the answers.